Hello, precalculus class. Today we're going to start our matrices unit with a bit of work of systems of equations. You guys solved these kinds of problems back in both Algebra 1 and Algebra 2 class. So we'll start with some two-variable review problems today, and then tomorrow we'll work on three-variable systems of equation problems and multi-variable system of equation problems. Go ahead and do this warm-up now. All right, the first thing that I did was assign some variables. We have two kinds of tickets. We have regular tickets, which are $8 each, and then we have senior tickets, which are $6 each. If they took in $35.80 in revenue, my first equation can be 8 times each of the regular tickets sold plus $6 times each of the senior tickets sold should bring in $35.80. Also, in total, 525 tickets were sold. So that means the sum of the regular tickets plus the senior tickets is 525 tickets. Once we have a system of two variable equations, we can solve it. We're going to spend time kind of reviewing the processes for doing this in this lesson, but hopefully you remember some of this. I used the elimination method over here. The first equation I did not change. The second equation, I took the whole thing and multiplied it by -6. The reason why I did that is I wanted to have a match with a different sign in one of the two variables. So I chose the y variable to have my match. So if you multiply the whole thing by -6, you're allowed to do that. It's staying in balance. So you get -6x, -6y, and -6 times 525 is -3150. Then we can add these two equations together, and by doing so we eliminate the y variable. We're left with 2x equals 430, which is very simple to solve. You get x, or regular tickets. There was 215 sold. Then I can use either one equation. I use the second one. 525 minus 215 leaves me 310 senior tickets, remembering what x and y represented. So this is a nice example problem using systems of equations. This graphic is really helpful. So remember that a solution to a system of equations consists of the values for the variables that solves all equations in the system. So you're trying to find the points that satisfy both equations. And depending on the system you have, there's different types of solutions or number of solutions. If you have what we call a consistent system, where the equations are independent, then they're intersecting and you have one solution. If you have lines that are parallel, so each of these represent a two-variable equation, then this system is considered inconsistent because there is no solution. So the idea of consistent or inconsistent has to do whether there's a solution or not. And then this situation is also that they're independent equations. That means there's two different equations. So you've got two different lines. Here it was independent equations. You have two different lines. But in this situation, these lines don't intersect. So there are no solutions in common, and we have no solution. The third situation you can have are when the lines are coincident, which means they are the same line. This situation is all points on those two lines, since they are the same line, are solutions to both of them, which means we have an infinite number of solutions. Once again, because they're solutions, this is a consistent system. But because the lines are the same line, then these are dependent equations, not independent or separate equations. So just to recap, your system can be consistent, means it has a solution, or inconsistent, means it has no solution. Your system can have independent equations, which means they are two separate equations, or dependent equations, which means they are the same equation. So those are two separate choices, and the combinations are such where you can have one solution, no solutions, or an infinite number of solutions. This slide is just showing you some examples of systems of equations. So what we're focused on today is example A, where you have two variables and two equations. But and these are both linear equations where they're just linear x and linear y. But you can also have a system of nonlinear equations with 2 variables. You can have linear equations with 3 variables. You can have another system with 3 variables, but one of them only has 2. And then here we have 3 variables, but we're given 4 equations. So just note there's lots of different kinds of systems that we are going to be solving. All right, so there's 3 methods to solving a system of linear equations. The first is graphing, the next is substitution, and the third is elimination. Here you go as a graphing example. Go ahead and pause the video, graph both equations, and try and find the solution to the system. Note, if you use graph paper, you'll have a better chance of success. Graphing process is sometimes not as good, especially if you have non-integer answers. But go ahead and try it now. Okay, so here's your solution. First thing I did was get both equations into slope-intercept form by solving for y. In the first equation you have y equals 4x minus 6. So I plotted the y-intercept and I walked rise over run, up 4 over 1, up 4 over 1, up 4 over 1. And then in the second equation I did the same thing, solved it for y, plotted the y-intercept, and then walked the slope down 1 over 2, and bingo, I noticed right there is that point of intersection. This is a consistent system because there's a solution, and independent system because there is 2 independent equations. Note, my solution is 2, 2, and I should just double check real quick by plugging it into the equation and make sure it works. 8 minus 2 is 6, 2 plus 4 is 6. And with graphing, you should always double check by plugging it in. And that's the first one. Here is another example for you. And I'll just slide down the page a little bit. And I'm just going to show you this example all done. So here's the system of equations. Solve them both for y, plot them. The first one is plotted here. The second one is plotted here. Note, the answer is 3/7 negative 9/7. So this is why I actually had it done for us already because I didn't have graph paper. But do you think you'd really find that through graphing by hand? You could use your graphing calculator and do second calc intersect for graphing there, but I would not recommend when it's non-integer solutions to try and use the graphing method. So this is the drawback to this method. All right, so here is the same example, but we're going to solve it through substitution, which is a much better method. So substitution is when you take one equation, isolate a variable, and then substitute it into the other equation. This equation is set up for that because we actually have the y that can be isolated very quickly, and we end up with y equals 4x minus 3. Then I'm going to take that and plug it in here for the y variable. So let's rewrite the first equation. 2x plus 3. Now I substitute in my y value from this second equation, and that equals negative 3. Now I have one equation with one unknown. So let's go ahead and just solve this. Let's see, let's combine like terms, 14x, and add the 9, so you end up with a 6. So x equals 3/7. I am not going to find that by graphing. Once you have the x variable, then you can plug it into either equation. So I think I'll use the first one. So the second equation, 4 times 3/7 minus y equals 3. So we end up with 12/7 minus y equals 3. So y equals 12/7 minus, if we need to get sevenths, 21/7, right? That's minus 3. And we end up with y equals negative 9/7. And then to check our work, of course, we could take both of these and plug it into the first equation and make sure it makes sense. So we might as well do that. 2 times 3/7 is 6/7. And 3 times negative 9/7 is negative 27/7. So we end up with, let's see, negative 21/7, which, yes, that's negative 3. So we know we did it right. That's substitution. All right. All right, so our last method is the elimination method, which I showed you in the warm-up as well, but we're just going to do another example. Note the rules. These are pretty detailed rules, and the reason why I actually list these here is they're going to lead into kind of the culmination of this unit, which is using matrices and something called row operations to solve a system. And really what matrices row operations is doing is the elimination method. So note our rules. Number 1, we can interchange any two equations, which we don't really use with a 2-variable system. We can multiply or divide each side of an equation by the same non-zero constant, so by any number that's not 0. And we can replace any equation in the system by the sum or difference of that equation and a non-zero multiple of any other equation in the system. This is a real complicated way to say that we can add the two equations or subtract the two equations together, which is what we do in elimination. All right, so let's go through and solve this problem. The first thing I am going to do is rewrite the first equation here because I don't like the fraction over there. So I'm going to multiply both sides by 3. You end up with 6x plus 12y equals 2. And then we have 3x minus 5y equals negative 10. I just rewrote the second one. So right now I don't have a match between either the x or the y coefficients, but I can see that if I multiply the second equation by negative 2, it will become a negative 6. And when I add them together, that first variable x will disappear. So I'm going to rewrite both of them. So this first one had been multiplied by 3, and we already got this. And then the second equation, I am going to multiply by negative 2. So you end up with negative 6x plus 10y equals 20. Right? Check your signs. Negative 5 times negative 2, negative 10 times negative 2. And then when we add these two equations together, the x drops away and we have 22y equals 22. Isn't that nice? Y is 1. So we have part of our system. Now let's plug it in and find the answer to x. So I think I'll use the second equation. 3x minus 5 equals negative 10. 3x equals negative 5. So x is negative 5/3. And there is our solution, negative 5/3, comma 1. So once again, we have a consistent independent system with one solution. So what would happen if you didn't have a consistent independent system? Well, so if your system ends up being inconsistent, you're going to end up with, when you're solving, at some point a false statement, and then you know there's no solution. Or let's say when you're solving, you end up with some sort of identity statement. 3x equals 3x, 2 equals 2. Then the equations are dependent and you end up with the same equation and there is an infinite number of solutions. And then you have to express the solution as an equation, one variable in terms of the other. No, that would be a situation where really the two equations are multiples of each other. So that might be one and the other one might be this. So you can see that the one equation is just the negative 2 multiple of the first. So in that situation, you can see right away that those are the same equations. More often than not, it's a situation where you have standard form and then the slope-intercept form. So they look very different, but they turn out to be the same equation when you simplify the standard form into slope-intercept. One of the things that gives students a hard time with systems of equations are word problems. So this is a very typical distance equals rate times time word problem. Why don't you pause it and give it a try on your own, and then I will go through the solution. All right, here's a start. I actually said distance equals rate times time, and you really don't even need that with this problem. This is just speed. So flying with the wind, a plane went 183 kilometers per hour. So my two variables are speed of plane, and that's kind of the speed relative to the ground, and then the wind speed. So with the wind, it's the speed of the plane plus the wind speed. And against the wind, it's speed of the plane minus the wind speed. This is assuming the wind is head on to the plane or right at the tail. And you can see this is really set up for a system of equations. So when I add these together, the wind speed drops out. You have 2s equals 324. Divide by 2. You end up with the speed of the plane is 162 kilometers per hour. So I can quickly subtract 183 minus 162, and our wind speed is 21 kilometers per hour. So pretty straightforward. Speed or distance equals rate times time problem. This is what we call a mixture problem, and I actually solved this two different ways. The first way I'll do it as a systems of two variable equations, but the second way I like better whenever I'm given a mixture problem, so I'll show you that as well. So the first thing I have is I need to know how many liters of a 10% acid solution, so I'm going to call that X for the unknown liters of 10%, should be mixed with 30 liters, so that's known, of a 50% acid solution to get some number of liters of a 20% acid solution. So that's going to be Y is the number I'm looking for. So my first equation is going to be the number of liters, X, plus 30 liters is going to get me Y. So those are kind of, I don't know how many liters I'm adding to the 30 liters of 50% acid solution. The next part of the equation is going to be your kind of weighted average. So if I have X liters at 10% and 30 liters at 50%, when they're done, I am going to have Y liters at 20%. And there's my second equation. So what I'm going to do now is you can go ahead and solve this system. I will pause it and do that as well. All right, so here's the solution. I used substitution since Y was already isolated here. So the first thing I did was multiply 0.5 times 30 and you get 15. And then I distributed the 0.2 on the X plus 30. So you end up with 0.2x plus 6, and then I combined like terms. I subtracted the 6, subtracted the 0.1x, and then I divided by 0.1. So we have 90 liters of the 10% acid solution, and when you're done, you end up with 120 liters of the 20% acid solution. So that is how you can use two variables to solve this. Now let's do this same problem again, but I'm going to show it where you can set it up as one variable. And I do this for mixture problems a lot. All right, so this method, I kind of create buckets. I have an unknown number of liters of the 10% solution, and I know I have 30 liters of the 50% solution, and I want, by the time I'm done, a 20% solution. So when you think about how much I have, I know it's going to be X plus 30. That was our Y variable when we set it up as a two variable. And then we can just write down our weighted average, 0.1x plus 50% of 30, which we had done before. And we end up with 0.2 times 30 plus x. And this is the equation we got when we combined them through substitution from the beginning. And if we recall our solution, we end up with this. We had 0.1x equals 9, so x was 90 liters. That's it. Go ahead and try your homework on two variable systems of linear equations.